As the title says, the topic of my thesis is, am I loud enough? You can hear me? Okay. Integrated imaging through 3D geophysical inversion, multivariate feature extraction, and spectral feature selection. In this study, new methodologies are presented for 3D integrated interpretation of multiple geophysical images for gold exploration. 3D inverse modeling of multiple geophysical data, multivariate statistics, and machine learning methods are used in this study. Discovery rate of major ore bodies had been falling from the early 70s onward. The depth of discovery was mostly shallow and has remained on the average the same up to now. Therefore, major challenges for mineral exploration in future will be deep targeting of hidden resources. New developments in geophysical instrumentations and modeling algorithms provide a way to access the deep targets. However, instead of lithotypes or metal grades, 3D inverse modeling algorithms produce 3D estimated images of physical properties. So it is important to extract the relevant geological features from geophysical images in an integrated methodology. The interpretation gets even more complicated when we try to combine 3D geophysical images, because by doing so, we increase the dimensionality of geophysical images. Therefore, it is important to develop proper tools to extract and put together geophysical patterns from these hyperdimensional model parameters. I address this demand through 3 stages. Integrated geophysical modeling in chapter 2 and 3 of this thesis. Challenges related to 3D inverse modeling of multiple geophysical data is presented. Because in order to perform an integrated geological interpretation, we need to have reliable 3D physical property images. In chapter 4, 3D statistical tool is presented for geological feature extraction from multiple geophysical multiple physical property images. And finally, in chapter 5, a feature selection algorithm is presented that combines the relevant extracted features to produce a consistent 3D geological model based on available known geological information. Please note that due to limited time, I only have to present the most important topics. The core problem is presented schematically in this slide. Different geological patterns respond differently to geophysical measurement. The problem gets more complicated when we introduce alteration and mineralization overprints, because they coexist on the same spatial domain as background geology, and this eventually modifies the measured signals. Different geophysical methods are sensitive, therefore, to different geophysical patterns, and sometimes a combination of several geological patterns are reflected on geophysical measurements. The key question is that how we could reliably estimate physical properties, and then how we could separate the hidden geological patterns, and then how we could put together the extracted patterns to reconstruct a geological model. At the beginning, we usually have access to two sources of information: non-geological information versus multiple geophysical data sets. Non-geological information, geological information are usually in the form of borehole data sets and are incomplete, sparse, and expensive to get. In contrast, geophysical surveys are complete, regular, and cost-effective. Therefore, they provide a way to calculate the 3D physical properties of subsequent interpretations. Please note that the 3D physical property models can be updated by non-geological information. For example, here we try to do several 3D inversion and we produce 3D physical properties. We can modify these 3D physical properties with already known information that can be geological information or other geophysical models. Through this, we address the first question. That is the topic of the chapter 2 and 3 of this thesis. The second question is addressed through 3D feature extraction. The presented numerical tool here provides a way to separate the overlapped geological sources inside physical property images. This is the topic of chapter 4 of this thesis. And finally, through feature selection, we address the third question. We present a 3D spectral learning algorithm that is supervised by available geological information to predict and reconstruct geological targets. And this is the topic of the last chapter of this thesis. We tested our methodologies on an epithermal gold-silver deposit in British Columbia, central British Columbia. We use data from this site because in sense of geological understanding and geophysical data, it provides us with one of the most complete geological and geophysical data sets. As can be seen, several gold deposits are located in central British Columbia, and Newton deposit is one of them. Gold-silver mineralization is located inside this rectangle, as you can see here, and is associated with Cretaceous volcanic rocks, the dark green color. Amark company acquired the property in 2009, and they find an estimated inferred mineral resource of 111.5 million ton with an average grade of 0.44 gram per ton gold. A bedrock geology map of the property is also compiled from borehole samples. As can be seen on the bottom of the legend, the oldest rocks are layered volcano-sedimentary rocks that are intruded by felsic to intermediate porphyritic intrusions, the pink color. And the younger dioritic intrusion, the red color, is presented in northwest. Based on drill core data sets, we created 3D models of lithology and alteration assemblages. A cross-section of these 3D models are presented here. As can be seen here, gold enrichments are located from shallow to nearly 600 meters depths, mostly inside felsic volcanic rocks. Alteration model also shows that the mineralization is inside this quartz sericite zone. The deposit is also offset by Newton Hill fault, NHF, which displaces the geology of mineralization by about 300 meters of normal deep slip movement. Geotech acquired the aeromagnetic data as a part of the combined magnetic and EM survey carried out between January to February 2010 on behalf of Amark. The ZTEM data, that is the Z-Tipper electromagnetic data sets, are interpreted by our colleagues from University of Alberta, and the magnetic data sets are used in this study. We also use airborne gamma ray data sets that are used in this study. We also use airborne gamma data set from Geological Survey of Canada in the form of potassium, thorium, and uranium radionuclide concentrations. A DC resistivity and IP survey of 85 line kilometers over Newton Hill area using the pole-dipole electroconfiguration was also conducted in 2010. Magnetic susceptibility of more than 9,000 core samples are also measured from 80 drill holes in the Newton Hill area through a TerraPlus magnetometer. The gamma ray spectra of 514 drill cores are also measured from 12 boreholes using radiation solution meter. The observed geophysical anomalies are magnetic total field intensities on regional and deposit scales, apparent electrical resistivities, and apparent IP chargeabilities, and radionuclide concentrations that are displayed as red, green, blue images, RGB images. As can be seen on the RGB images, Red indicates potassium, green indicates thorium, and blue indicates uranium. The white area that is combination of all three colors indicate high concentrations of all three radionuclides. The right figure also here, the right one on the bottom, provides a better way to visualize gamma ray with ratios of radionuclides. So red is therefore the ratio of potassium per thorium, green is the thorium per uranium, and blue is the uranium per potassium. As can be seen, this northwest southeast trend over porphyritic intrusions at the center and felsic volcanic rocks indicate high concentrations of potassium due to the presence of potassium-rich phyllosilicates in hydrothermal alteration zone. That is actually quartz alteration. Gamma ray measurements on drill core samples also confirm the highest concentrations of potassium in quartz altered felsic rocks. That are the host of the gold mineralization. Susceptibility readings of borehole samples are also presented in this horizontal slice of the 3D susceptibility model to compare with bedrock geology. As can be seen in both plan view and cross-section, most magnetic rocks are related to mafic volcanic rocks and diuretic intrusions. Felsic volcanic rocks and porphyritic intrusions show lowest magnetic susceptibilities. Gold enrichment is also linked to low susceptibilities of felsic volcanic rocks. As can be seen on the diagram, for susceptibilities of more than 5 milli-SI, the gold concentrations are less than the desired cutoff factor. That means by increasing the susceptibility, gold is decreased. So gold mineralization is mostly occurred in the low susceptibility zone. The results of preliminary 3D inversion of DC IP data on the prospect scale is presented here. The low resistivity zone with NWSE, northwest-southeast trend, is probably related to the low resistive phyllosilicates and sulfide concentrations of the epithermal system that is confined by a high resistivity periphery. A chargeability high on the bottom, a chargeability high zone also coincides with the low resistivity zone and is related to disseminated sulfide concentrations in the area of hydrothermal alteration. In deposit scale, finer details of epithermal systems are recovered through 3D inversion. The periphery deposit exhibit large resistivities and low chargeabilities. A moderately high resistivity, low chargeability zone is also visible inside a northwest-southeast conductive zone. That means this high resistive zone, and also low chargeability zone here. The location of this zone on the map is right beneath the peak of the Newton Hill fault, as we can see the topography on the top right figure. Is associated, and this suggests that this zone is probably associated with pore spaces filled with quartz in gold enrichment zone. The recovered chargeabilities also exhibit a link with susceptibilities. Felsic to intermediate porphyritic intrusions and felsic volcanic rocks show low chargeabilities and susceptibilities, and mafic volcanic rocks and diuretic intrusions show high chargeabilities and high susceptibilities. This relationship suggests that we can use IP chargeability to constrain the magnetic inversion to increase the accuracy of magnetic susceptibility model. We use a cooperative strategy to constrain the magnetic inversion with information derived from 3D DCIP inversion. This eventually helps to increase the accuracy of the magnetic inversion. In this case, we merely assume the influence of the IP-driven model on the cooperative inversion is evenly distributed in X and Y direction. A constant global weight determines the balance of information flow from the DCIP inversion to the magnetic inversion, magnetic cooperative inversion. When W is equal to 1, The IP-driven model and the resulting cooperative susceptibility model are equivalent. When W is equal to 0, the influence of DC-IP inversion is also 0, and the cooperative inversion is equivalent to an unconstrained inversion. Updating the global weight doesn't actually reveal low susceptibilities of the porphyritic intrusions and felsic volcanic rocks, the host rock of mineralization. Therefore, we incorporated a more realistic weighting method. In this stage, since the relation between IP chargeabilities and magnetic susceptibilities are visibly not a perfect linear link, this suggests that some places in 3D inversion of magnetic data need to be kept away from DC IP influence. When we look at the magnetic response of the IP model, it is very similar to the magnetic response of measured data. However, in some places there are some discrepancies. The point is that we only want DC IP information to be used in magnetic inversion if and only if there is a link between them. Therefore, in places with more similarities between these two maps, we are able to let DC IP modify the magnetic susceptibilities. And in some places with less similarities, the inversion procedure is forced to get susceptibility information from observed total field intensities. To do so, we produce a non-uniform weighting model that is based on the multiplication of these two maps after standardization. The standardization rescales the 2D images to have a mean of 0 and a standard deviation of 1. When we multiply the standardized maps, we could have a similarity measure to produce a weighting model. The weights are then scaled from 0 to 1. Low weights mean less influence from DC-IP inversion, and high weights mean more influence from DC-IP inversion. The non-uniform inversion results are presented here. As can be seen, this global weighting W equal to 0.01 in the middle produces a more realistic susceptibility model that maps both high susceptibilities of mafic volcanic rocks and also diuretic intrusions, as well as low susceptibilities of felsic volcanic rocks and porphyritic intrusions. The unconstrained and cooperative susceptibility results are evaluated by measured susceptibilities of borehole samples. As can be seen on the right, the cooperative inversion has produced more accurate 3D susceptibility model compared to the unconstrained inversion on the left. Through integrated interpretation, 4 petrophysical domains are inferred from cross-correlation of physical properties. Domain 1 is a low chargeability and low susceptibility zone related to the porphyritic intrusion with variable resistivity values. Domain 2 is a low resistivity and high chargeability zone with variable susceptibility values related to the sulfide dissemination. Domain 3 is also a copper-rich zone with high susceptibilities and chargeabilities and low resistivities due to the presence of more magnetite-bearing rocks and sulfides. And finally, domain 4 is also a gold, silver, copper-rich zone with low susceptibilities, low chargeabilities, and high resistivities due to silicifications. Therefore, we address the first question through cooperative inversion of DC-IP and magnetic data. In Chapter 2 and 3, the next important question is how to detect geological patterns from the estimated 3D physical properties. We present a solution for this in Chapter 4 through a statistical feature extraction method using independent component analysis. The core idea in ICA, or independent component analysis, comes from central limit theorem in statistics, which states the distribution of a sum of independent random variables tends toward a Gaussian distribution. The idea behind ICA is that we can go in reverse direction and recover the latent non-Gaussian independent components through maximization of non-Gaussianity. This suggests that we can separate overlapped geological patterns inside multiple 3D physical property images. There are several statistical measures of non-Gaussianity, and different algorithms are available to approximate them, like skewness, kurtices, and negentropy. We showed in this thesis, that the negentropy maximization is more stable and more accurate algorithm for 3D source separation compared to other methods. In this study, a 3D MATLAB code is presented for 3D geological feature extraction that is based on fast ICA algorithm through negentropy maximization. The fast ICA algorithm was first introduced by Hivarinen in 2001. In this study, open source MATLAB functions are provided by Brian Moore in mathworks.com, but the 3D coding and hybridization of the algorithm is done by myself. We showed that the fast independent component analysis is a robust method for geological feature extraction that seeks to extract latent geological features inside multiple physical property images. We used negentropy maximization as a mean to maximize the non-Gaussianity of geophysical images. We simulated this method to understand how the feature extraction works. The idea behind negentropy maximization is the definition of entropy in information theory. Negentropy is the inverse of entropy. The probability density of a population with low entropy shows distinct patterns. That means, for example, in a world with low entropy, patterns are discernible. But in a world with high entropy, patterns start to shrink and disappear. The point is that if we could a way to approximate the negentropy of physical property images and maximize it, we will be able to extract the latent geological features or patterns. This eventually helps machine learning or visual interpretations to better classify and extract patterns for future pattern recognitions. We simulated and evaluated our methodology on a 3D complex geological model with two overlapped alteration overprints. We used NODE program for 3D geological modeling. The background lithological model, the L1, consists of 4 distinct lithotypes that are affected by 2 alteration overprints, L2 and L3. The geology model has passed several faulting and folding, dike intrusions, shear deformation, and alteration overprints. The reason why we use this complex geological model was because of the general principle behind negentropy maximization. That is a topic in information theory and complexity theory. According to a theorem similar to central limit theorem, the spatial complexities of physical property images are equal to or greater than that of the least complex geological features. This general principle enables us to maximize non-Gaussianity of physical properties through negentropy maximization. To do this, we need to have sufficiently complex 3D geophysical images and thus a complex 3D geological model. A mixture of 4 background rock units, L1, and 2 alteration events, L2 and L3, correspond to 3 main physical property distributions, including electrical resistivity, IV chargeabilities, and magnetic susceptibilities, as can be seen here. The first row is the resistivity, M is the chargeability, and kappa is the magnetic susceptibility. This equation means that, for example, the background geology L1 comprises 90% of electrical resistivities, and the rest of the resistivities come from the 2 alteration events. For example, 5% from L2 and 5% from L3. By 90% right here, 90% of resistivity comes from L1, 5% from L2, and from L3. The same for all other resistivities. So this mixing matrix helps us to convert geology to petrophysics. And which means, for example, we also add an additional non-Gaussian noise to the model to test the effect of the unpredictable noise on feature extraction algorithm. We explain more in the text. We explained more in the text that the negentropy maximization is superior to Curtis's maximization and other techniques, because Curtis maximization, for example, is not stable when we introduce even a slight amount of noisy outliers. The 3D physical property models are presented here with their histograms. As can be seen from 3D models and also histograms, it is very hard to separate the background geology from alteration over prints visually. Even traditional statistical tools are not able to separate these latent sources. Therefore, we present a method to do that. Geological sources naturally comprise the physical properties of rocks. The physical properties emanate natural geological fields that can be measured as geophysical signals on Earth's surface. Then, through inversion, we try to reconstruct physical properties in 3D. Most geophysical studies stop here and try to interpret the physical property images visually, or at best with rather simple statistical tools. In this study, we propose another step to extract the hidden geological sources from estimated physical property images automatically. As can be seen, 3 sets of geophysical data are synthesized through forward modeling. Through inversion, we recover approximated 3D physical property images. In this article, we already explained why traditional source separation methods fail to recover the original geological features. As can be seen here, the negentropy maximization successfully recovered the latent geological features, even if we introduce the noisy outliers to physical properties. The first independent components, for example here, it takes the first alteration event, and the second independent component here, negentropy independent component here, detects the second alteration event, and the background geological pattern is detected in the third one. Something that is not possible by visual looking at physical properties. Therefore, we address the second question. But please note that since the ICA is a blind source separation method, it means we don't use non-geological information to decide what is the meaning of each extracted independent component. We use machine learning methods to compensate this limitation through an advanced feature selection algorithm. Through this, we answer to the third question, which is how to put together the extracted patterns to recreate and predict geology based on the incomplete set of non-geological information. Our proposed algorithm is a 3D hybrid intelligent system that we call it 3D Spectral Feature Subset Selection. It works on the basis of several dimensionality increase and dimensionality reductions to extract and select the relevant features that are related to specific geological patterns. The whole idea is similar to what we did until Chapter 4. We do several 3D inversions to provide 3D physical properties. Then, through ICA, we extract the independent components. In this stage, we use a continuous wavelet transform to decompose the 3D independent component images into several raw spectral features. This decomposition eventually helps to separate more overlapped features that are remained in each independent component. Then the algorithm uses again the ICA to separate the frequency-dependent features, to extract independent spectral features to be fed into the machine learning procedure. The spectral feature subset selection algorithm is based on a multi-layer perceptron model of neural networks. The inputs of the network are extracted independent spectral features. A biobjective genetic algorithm optimizes the output of the network through simultaneous adjustment of the network weights, W's here in this picture, and the different combinations of the input features. Therefore, it is able to decide which sets of input features produce the best predictions. Traditionally, neural networks are not able to tackle this issue, and they use all of the inputs for predictions. And this results in misleading predictions, since some of the input features are always irrelevant to targets we want to predict. As can be seen, several phases of dimensionality increase and reductions happens during feature selection process. The whole idea is that through expansion of geophysical space, the algorithm tries to extract independent geological patterns, and then the machine learning tries to link those patterns to geological targets through feature subset selection, which is actually an intelligent dimensionality reduction. So through feature subset selection, we label our features. Which features is, for example, granite, which feature is basalt, or which feature is gold-rich zone, like that. Please note that the green dimensionality reductions on the slide are based on ICA. Since ICA is a black box dimensionality reduction method, this is not recommended to use it here unless we face computational and hardware limitations. Sometimes the 3D raw spectral features are too heavy for normal computers with 16 or even 32 gigabyte of RAM. So we have to reduce the dimensionality of features anyway with ICA a little bit. In this study, 3D codes 3D coding is performed in MATLAB environment, and open source MATLAB functions are provided by Brian Moore in MathWorks and also Faradas in MATLAB site. The 3D coding of the hybrid system is also done by myself. Since the 3D algorithm is very slow for preliminary evaluations and testing stages, I wrote an equivalent 2D code for the purpose of testing and evaluating the algorithm, as well as to compare it to the traditional artificial neural network to see if it works or not. The spectral feature selection process is simulated on 2D for feature extraction and feature selection procedures. The input of the features of the selection consists of 3 standard images that contain mixed forms of latent features, 2 human faces and 1 cat face. These are standard images that are used in numerous image processing articles and book chapters in the last 2 decades. The problem can be, I use these photos because we already know what is a cat. We have an idea. So if I use, for example, geological targets, our brain cannot work with that. Okay, the problem can be formulated as separation of cat's face from mixed images with limited access to the data from the original cat's face. Targets are sampled in 2 horizontal and vertical directions, pixel by pixel. So, for example, in this direction, we only have limited information about cat's face. So the question is how we can reconstruct the face of cat from mixed images and also from known information. We use continuous Weyl transform for spectral decomposition of independent component images. Although Fourier transform is a powerful tool for image decomposition, but it does not represent abrupt changes efficiently. In fact, Fourier transform is not spatially localized because the data in Fourier transform are represented in the form of sine waves, and these sine waves oscillate forever in any given direction. In contrast, wavelets are localized in space and also time, but here I only use a space, and have finite duration. Therefore, the output of wavelet decomposition more efficiently reflect the abrupt changes in images. That makes it an ideal tool for feature extraction. This is an example of 1D continuous wavelet transform with 3D representation, in which the mother wavelet is shifting and scaling in only one direction, that is in the x direction, horizontal direction. Scale is actually inversely proportional to frequency. Larger scale factors are corresponding to large expanded mother wavelets and low frequencies. As can be seen in different frequencies, different features are detectable. Scaling and shifting the mother wavelet in other directions also reveal other sets of features. Here is an example of that. Here is a high frequency example of the extractable features in different directions of mother wavelet shifting. As can be seen, the video shows when angles are changing. During the change of the angles, different patterns are appearing here. Therefore, the 2D spectral feature extraction starts from separation of latent features by ICA. Through ICA, phases are separated to some extent. However, there still remains several overlap features. Continuous wavelet transform helps to decompose the independent components to separate the frequency-dependent features. We calculated the 2D wavelet coefficients for 20 scales in 4 directions. However, the algorithm allows choosing any number of scales and directions as long as the computer hardware and specifications allow. The resulting 240 raw spectral features are passed through an ICA dimensionality reduction. You remember the hardware limitation to extract 123 independent spectral features. The extracted features are then fed into the machine learning feature selection algorithm. This is the end of the feature extraction process. The 2D spectral feature learning takes the extracted features, the extracted independent spectral features, and through a genetic algorithm optimization train the neural network with limited known information about cat. 25% of known information are kept for training evaluation. As can be seen, the spectral learning results are superior to the results of the conventional artificial neural network. This is because of the ability of feature subset selection algorithm in selection of relevant features related to cat's face reconstruction. The feature subset selection error landscape on the left also shows that after 5 generations of genetic algorithm, 54 features are selected and gives us the 94% correlation coefficient at the end. The image reconstruction through feature subset selection is obviously superior, therefore, to the conventional neural networks. 5% of the known information are kept for testing here to see if our predictions are good enough. The feature subset selection picks the 54 relevant features for spectral learning, and this selective strategy eventually results in more stable predictions. As can be seen, the cat's face on the bottom is more visible by feature subset selection rather than traditional neural network. Please note that increasing the size of the image enormously increase the computational cost. That's why I use small images here. If I was using HD images, it My computer was going to blow. So, okay. Therefore, 54 out of 123 features are relevant, and the rest of them are redundant. So feature selection is able to detect those redundancy and relevancy. For practical implementation, the practical implementation of the spectral feature subset selection is proposed as a 3D MATLAB code for geological target estimation over Newton gold-silver deposit. The 3D procedure here is similar to the 2D algorithms used in the previous section, except that the calculation of raw spectral features are iterated for all horizontal slices. The conventional interpolation of borehole data sets suffers from lack of spatial information in places without borehole coverage. As a result, the traditional interpolation methods are not able to add new geological information in places without borehole data. In this study, we show that the feature subset selection algorithm is able to compare the geophysical images to geological targets and learn how to reconstruct the targets from 3D physical properties. The physical property models are derived from cooperative inversion of magnetic and DCIP datasets in Chapter 2. A preliminary FastICA separates the latent features inside the multiple physical property images. The results are shown in this in the figure on the bottom, in the form of three negentropy optimized independent components. The separated images are combined as RGB images, red, green, blue, and can be seen as an animation from deep to shallow. Again, like this. The question is how we could reconstruct 3D gold grades from these rich sources of features. To extract the spectral features, three independent components are decomposed to form a set of raw spectral features through continuous wavelet transform. We calculated the 2D wavelet coefficients for 5 scales and in 12 directions. That means every 30 degrees. Therefore, 360 3D raw spectral features are produced that are presented from deep to shallow here. Can be seen, it's like an animation here. The 3D models are sliced at the elevation of 1,000 meters, and this is a plan view, actually. The dimensionality of raw spectral features is also reduced to 108 features to take care of the computational cost. The extracted independent spectral features are compared to the limited geological targets, that is the gold concentrations, and through genetic algorithm, the network learns to predict gold concentrations from extracted features. 70% of the targets are used for training. 25% of them are kept randomly for training evaluation, and 5% of them of the non-information are also kept for testing. As can be seen, the spectral learning is much more efficient than a conventional neural network, compared to 33% to 85%. The error landscape on the left also shows that the best results are obtained. This error landscape indicates by objective genetic algorithm optimization. Because here we don't have one single curve for error. We have a two-dimensional error. Okay, as can be seen, the spectral learning is much more efficient than conventional neural network. The error landscape shows that the best results obtained in the last generation or after 20 iterations, with maximum 98 number of selected features. The predicted gold concentrations are tested with 5% of the remaining borrow samples. As can be seen, the predictions of feature subset selection method is much better than conventional neural network. The feature subset selection selected 96 out of 108 features, which means 12 spectral features were extremely redundant in prediction of gold concentrations. The proposed algorithm in this study also presents the selected features that are linked to gold distribution, in addition to the predicted gold grades. We also used borehole lithotypes to train the feature surface selection algorithm. Again, the algorithm gave better results with 78 features out of 120 features. The feature selection reconstructed a more consistent lithotype model compared to traditional interpolation methods and conventional neural network. The diuretic intrusion is mapped clearly as red color, and the mafic rocks are presented as green. The blue color indicates the felsic rocks that are hosts of the gold mineralization. And here is for all depth from deep to shallow, the lithotypes predictions are also presented. Therefore, the proposed methodology here provides a way to automatically reconstruct geology from geophysical data and from limited non-geological information. Therefore, we address the third question in the last chapter of this thesis, and this is the end of my Ph.D. research. Thank you.
Thank you very much, Berman. So we enter a period of question. Vous m'entendez à Paris et à Montréal?
Should I thanks after that?
Oui, oui. Oui, on t'entend très bien. Oui, tout va bien. Yes, if you have to finish by thinking. Yes, go on.
Okay. This work is funded by a strategic projects grant from Natural Sciences and Engineering Research Council of Canada, and also Fonds de Recherche Nature et Technologie du Québec. I also thank our colleagues from University of Alberta, AMARC Company in British Columbia, and Geotech Company. Specifically, our co-authors in scientific journals, Jeremy Richards, Julian Hubbard, and Jean Ligo, and Mark Rebaliati, and Ken Witherly. I especially thanks my wonderful supervisor, Dr. Cheng, here, for her excellent helps and directions during my PhD program.
Thank you.
This is actually good.
You can let the Poincaré station,
Yep.
Take some time to read it. Okay, so we enter a period of question. On entre dans une période de questions et la